with the existence of a kernel with
O kappa
equals to kappa plus. Or kappa.
Thank you for attending, and I need chalks. Okay, so the context is VFC, and since we deal with the infinite exponential partition relations, we need to restrict ourselves to definable functions only. Okay, and it is well known that AC contradicts partition relation with the exponent, with infinite exponent. So there were partition relations related to measurable cardinals in the with choiceless models, but here there was a result by Yechiel Kimchi, the first one, not exactly the first one, but directly with measurable cardinals. Yechiel Kimchi at 78, he proved that the existence of measurable cardinal, there is kappa, O kappa equals 1. O kappa is Mitchell's order hierarchy of measurable cardinals, is equiconsistent with the following partition relation with definable functions F1 to omega exponent to omega F0. So I will add at the beginning def just to emphasize that these are definable functions. So for any definable functions on omega sequences of F1 of countable ordinals, there is an omega sequence which is homogeneous in the coloring. So this is the infinite exponent here. So a simple naive extension of this would be what happens for O kappa equals n or even alpha, and maybe it is equiconsistent with aleph 1 omega to the alpha, omega to the alpha, aleph 0.
When you say definable, do you mean definable from ordinals or?
Ordinal definable.
Okay.
Yes. And now the technique here for Yechiel Kimchi was to use one direction, to use pre-reinforcing, and the other direction he used LB. So you have a definable function and find for a specific definable function, the homogeneous sequence will actually show that there is a measurable cardinal in LU. So the obvious generalization here, if we want to go far on alpha, will be to use reinforcing in one direction, and to use Mitchell's core model, and I use the notation Kn like Tech's book. In the prehistory it was K star, for maximal sequence of measures, and there is no maximal sequence of measures if O kappa equals kappa plus plus, so it is much higher than we need. So we really, we can really use it. But there are some simple problems here, and the first problem is that if alpha is greater than 1, then there are limit points. And limit points are bad because a limit point in reinforcing, at least, are measurable cardinals, and non-limit points are non-measurable. So you can always break the homogeneity by such appropriate coloring, definable coloring. So the first thing, now it's, well, it's not so, it will appear later on. So the first problem is limit points. So we restrict ourselves to open sequences. Now, in reinforcing, at least at the, let's say, medium level of reinforcing, if you take open sequences, it doesn't change much. It is still generic. By closing it, you can get the original ordinal sequence that you have. And if you are not much above O kappa equals kappa plus, then you still resurrect the measure sequences that reinforcing originally built on. So we can take open sequences. The second problem is the full homogeneity. Full homogeneity is just homogeneity. Take any subsequence, a subsequence of open sequence is open, and there is a problem because limit points have different characteristics. Even for omega cube, there are two kinds of limit points. The simple limit points are measurable cardinal. The second order limit points are measurable cardinal of order 2. Again, it will break definability, homogeneity. So apparently it goes not only this problem, but it goes that problem. For the lower level of reinforcing, not all subsequences are generic. I mean, for the full, any subsequence is generic, you need repeat point and something hypermeasures and things like that. So since we are looking for generic sequence that will hold that will be the homogeneous sequence, we have to limit ourselves also on the other direction. Now, to present this, I will give a few definitions. So let's take as a sequence cofinal in kappa and define the following. S0 will be its S union of its closure, because I want clubs. I still want clubs. And for beta beta successor, I just take S beta, the derivative of this, and for a delta limit, I will take S delta to be, well, first just the intersection of S beta, beta less than delta. This works up to kappa. Then we need to take cofinal sequences, which I will update it. I will keep it because I will also restate later. So now what happens here at reinforcing, so for reinforcing, if G is generic over R alpha, meaning O kappa equals alpha, then any subsequence that is a club, but satisfies also that H beta, well, I haven't defined it, I will immediately. Now here, there is a side issue here that without the parentheses, S beta will be always S beta minus S beta plus 1. So the points that are exactly of order beta. So here, if you keep unit points at the same level of complexity, you may say, then it is a generic in rate enforcing, and it is kind of simple conclusion from Yechiel's result about rate enforcing, that you can break it to lower level and upper level, and that a generic sequence should be generic on the first part, and any cofinal sequence in kappa will be included, will intersect the generic sequence if and only if it is it contains as a final segment of the generic sequence. Sorry, it will be finally contained in the generic sequence if and only if it belongs to one of the measures that was used in the forcing. So this gives us at least up to kappa. And now we are ready to give the arguments, and I will give the arguments, although the theorem that I want to present is about kappa plus, but it is the same type of proof. So taking for this direction, I take R alpha, find a generic, let's call it generic alpha. The order type is of omega to the alpha of a generic sequence. And then I Levy collapse 2 to R alpha plus 2 aleph 1. This allows me within the internal, within the generic extension, to see all possible generic sequences, because everything is countable. And then within this model, I look internally at the. I'm sorry? Well, what I'm looking for, yeah, it is it 2 to the kappa? It's a little bit more. I want to make sure that I have everything, but I mean, I can take plus, etc. So the idea is looking at rate enforcing. I make a direct extension that force me for a given function, force me the value, and every subsequence will have and any generic sequence that is contained in such extension will have the same color. On the other side, when I have to look on all kind of omega to the alpha sequences, open sequences actually, this is what I'm interested with, and by induction on beta less than alpha and on mu less than kappa, I start working on omega sequences, omega square sequences, etc. And I define filters that contains final segments of such final segments of these segments, and I check inside Km whether this is, when I take limits of order omega to the beta, I call this potentially filter, whether it is normal ultrafilter on kappa or at a lower level. So I always, at stage beta, I will use all the results of gamma less than beta for the smaller cardinal. Now, the definable function basically says, if this is not an ultrafilter, then there are two sets that both are cofinal in the segments, and you take this is well ordered, so you take the minimal counter example, and you ask whether the first element is containing the one set or the other, and of course it won't be homogeneous. Oh, I'm sorry, I didn't mention that actually what we need is weak homogeneity. Namely, when I take a sequence, I just remove finitely many segments, and that's fine for the whole argument. And this, of course, because I don't have limit points, it also obeys this result. I mean, you don't change the complexity of limit points. So, and for sigma complete, you take the first counterexample of omega sets that have empty intersection, and you ask whether the first set contains the first element or not. And for normality, we cannot work, because normality, you may hit something that each one of the points here is sent to a different image. So homogeneity cannot work when these elements are separated. Actually, we are looking at a kind of indiscernibles. So if they are different, then you cannot do anything. But what you can do is make sure that this is a regressive function that is order preserving on the sequence. And if it is order preserving, then what we call dependent coloring, you give the original function, original sequence, a color that is that depends on the color that the image takes. Now there are two possibilities. If all regressive functions are bounded, this is fine because we would get weakly normal filter. But if it is unbounded, then we use dependent coloring. And this is somehow related to Rudin-Kissler orders of measurable. I mean, if everything works, then it just may say that what we have here is a kind of ultrafilter that is reflected, not really reflected, but that is compressed down. And now there comes a specific argument, because with weakly normal filters, it is not enough. So what we do is that we look based on the induction, the use by induction, what we can show, since this filter concentrates on the beta limit points, it actually means that we already have here the following property. The set of all mu less than kappa such that Km satisfies that O mu is greater or equal beta belongs to U beta. This is the property that we have, because the limit points were taken care before that. So, but we don't know what we want to have is that kappa has order greater than beta. So what we take is the following. We use the ultra power of less than kappa functions over U beta. No, let's do it here. We take Km with a shorter function with small image over U beta, because this is a weakly normal. And we take also Km with full ultrafilter. And we know that since it is not normal, it will, the identity will not be kappa or something like this. But what Mitchell proved was that Km actually, not just you have elementary embeddings, but that this is an iterated ultrapower. It can be defined as iterated ultrapower. So we follow the proof of it to represent, let's call it this I and this is J. So we try, this is N, we call N, and this will be N mu, and this will be N minus, and this is N minus mu. So we iterate it as the proof of Mitchell's proof goes, and then we have the remainder. At each point we have the remainder. Now this is the crucial point here, is that this is also elementary embeddable here, because we have function with small image versus function with big image, and we see that when you look at I kappa is the first element that is moved, because any function that has values less than kappa, here it should be bounded. Here it is not. So I kappa, where kappa goes here, is the critical point of K. Now, if we think about it, when we iterate it, the iteration at the beginning is the same up to when I kappa moves here and it doesn't move here. So this is a critical thing. The effect is that the iteration should not be one initial segment of the other, but they coincide until I kappa. And the idea is the following, to make it a very very condensed. I kappa is not moved here, but it has its measurability, which is at least I beta. But here I kappa is moved, and it is moved by a measure that appears here, which must be higher than beta in order to keep the result as a beta, measurable of order beta. So it proves that in Km, while iterating, and since the sequence of measures is absolute when there is no big measure, then you will really get the real order. It implies that in Km, O kappa is greater than beta. Okay? Now, what do we do about other, in order to push it upward? So, moment reflection shows, for instance, that for O kappa equals kappa, what we have is a fixed point. So we have a homogeneous set with a fixed point. So first you can put aleph 1, arrow, some mu as an ordinal, mu aleph 0, but actually you can replace it by exist mu less than aleph 1, such that this works. And you can push it a little bit higher, but then comes a problem of definability, because this was an explicit description, and what we need is implicit, like the Mitchell order, and also reinforcing is implicit, because this is why he took sets of sequences of measures. So what we do is we can take, to make things more common. We take square of kappa. So we have C alpha over limit alpha, let's call it kappa plus. And we use here not just intersection, but intersection according to beta I, where beta I less than beta I less than cofinality of delta, and we can take it from the sequence here, and when cofinality of delta is kappa, we take a diagonal intersection on I less than alpha for S beta I. Okay, so this is S theta. Now, together with this, we now have to say something about the order of this. So we expand or give a variation of Galvin-Heinel scale by taking the following. If I have S, then S0 will be still S. For beta plus 1, it will be the same. No, what I want is function. So f of 0 for alpha is 0. F of beta plus 1 of alpha is f of beta alpha plus 1, provided that alpha belongs to S beta including. And here we take the supremum of beta I less than cofinality delta over f beta I, and here we take the diagonal supremum beta I less than alpha for f beta I, f beta I on alpha. So this is how we define f delta alpha. And what we have here is that this property now, by induction, what we show here, that actually for beta larger than kappa, we can look at O of mu is greater than f of beta of mu, greater equal. And the same argument here, it shows that because when we have to when we move I kappa here, I kappa was already was decided by the J or by the I of f beta, which is f I beta for that. So, but by elementarity, this is reflected down, and since we get that it is better, it moves here, it must have at least one additional, measure than it has on the right hand more than the left hand. Then the result is that O kappa is greater than f is greater than beta, because the function is only on kappa. So it tells me, for instance, that for O kappa equals kappa plus kappa, it concentrates on mu, that O mu is mu plus mu, to show that, that it is kappa plus 1. It concentrates on such. So these are reflected here. And that is it. And for rate enforcing, it just works the same for O kappa. Still, we have the property here when you translate it to the functions here. So it is an equiconsistent.
Questions or comments?
Just a quick question, because it was asked about ordinal definability. So I guess there are no problems with relativization. So in Hod, I just have the partition relation like this without definability. Or are there some issues?
I don't know.
Yeah, that's the point. That's why I'm asking.
Yes. Okay. No.
So you mean
It is
Hod
true
is-
that Hod is not always relativized to Hod.
Or
Maybe
asking
downwards.
them. Asking
The
them.
homogeneous set.
I'm sorry.
The homogeneous set.
That would be the point.
Yeah,
So
it
this
is
the case of-
definable. I mean, you can. The partition in Hod. Okay.
It's ordinal, but it's not in hot. It's ordinal.
Oh, yeah.
But homogeneous.
Yeah, I don't know. An interesting extension is what happens for O kappa equals kappa plus 1. Then, in rate enforcing for O kappa equals kappa plus, you get regular cardinal, so you can collapse it to aleph 1 and then it follows. But it means that in rate enforcing, you get omega sequence of O mu equals mu plus. Each one of them can be collapsed to a regular cardinal. So actually you get a partition relation on aleph omega. It is equiconsistent. And you can push it up. I don't know what to do with the undefinable ordinals.
Thank you again. So this ends the session.